but if you it's like over radius at an angle of that. But for complex powers, you like one of these makes sense. Yeah, well, because and one of the things he told me, like especially when it's all the I almost ran out of time on the first finish. It's going to be a lot. Because the formula for complex powers is like, I want to find like power dissipated. Like if you do it faster, where you can say like, okay, there's a resistor, I know that reactor power, so I can't say it's like, and so I can't say it comes right I'm like, Boston, he comes over here and asks me questions. I don't care about it. But it's I can't write anything down with these recorders, so he's like on the third thing. The first day, like, with like this is this positive direction. Bro.
Any questions before I start?
When you had like a problem on the homework, am I right in saying you had to assume like TD mode? It was homework 8, where it's like the transmission line problem.
The wave guys.
Yeah, the wave guys.
Alright, he's asking a question about you assume the TE mode and a TE10. You don't assume that. What you have to do is and he's asking a specific question related to the quiz. So if you're given the cross-sectional dimensions of a guy, and this is A, and this is B, and we'll assume A is greater than B, so this is the long dimension, call it in the x-axis, and this would be in the y. This is just standard. So he's asking a question, how do you know what mode it's in? Do y'all follow me on this, class? Now this is fundamental, it's important. The lowest order mode a rectangular waveguide operates in is the 1-0 mode. Do y'all follow me? Now listen, so when you're calculating the modes, that's all it will assume. Well, you don't have to assume 0. You can put 1/2 square root of mu epsilon, and then it's square root of m over a squared plus n over b squared. Now that covers all the possible modes. But every time m and n are, either one is not 0, it can be either a TE or TM mode. For instance, when you have FC10, that can only be TE10. Do y'all follow me on that? When I have FC, this is the order they usually appear in, 20, that can only be TE20. If I have FC1, 1, that can be TE11, or it can be a TM1, 1. Either one. Do y'all follow me on this? So usually, the way you do these problems, and you should always do it, first you calculate the lowest order cutoff frequency, then the next cutoff frequency. Follow me on this? And you find the operational frequency. Now, almost always, but not always, almost always, the operational frequency is between the 1.0 and 2.0 modes, somewhere between those two. Do y'all follow me? And the 2.0 is twice the 1.0 frequency cutoff. So it's somewhere between there. If that was 6 gigahertz, this would be 12. Your operational frequency would be 8 to 10 gigahertz typically. That's how you do that problem.
And if it's between those three TVs.
Well, if it's above them, it could be 2.0. Remember, if the operational frequency is between 1.0 and 2.0, only the 1.0 mode can exist. Remember, this is a high. In order for the 2.0 to exist, you have to be higher than that frequency.
The 2.0 exists, no, you'll
You
also.
always have 1.0. That's the
as
problem.
well.
And that's the problem. If you operate in a frequency range above 2.0, now you have both the 1.0 and 2.0 existing concurrently, and no longer does your power go down the waveguide at the same velocity, because they're different velocities. Do y'all follow? It's real important you appreciate that fact. You never want two modes of operation. There's some exceptions, and I'm not gonna get into that. But primarily, you never want it, in my opinion. Okay, everybody on that? Now, did you have any other follow-up on that? Or?
No, it was wrong just about the TVs.
Okay. Anything else? Because I've got some stuff I want to cover today, but I don't want to just go racing through it. If anybody has any questions. All right, let me get rid of that. So today, back to antennas, and I'm going to back up a little. And what I'm trying to do is teach this to you the way I would want it taught to me. And there's a lot of things I'm about to say that aren't going to make a whole lot of sense in terms of their importance until we keep going through this. Then it all comes together. I don't know if you appreciate this, but when I did the waveguide thing, starting with Maxwell's equations for the rectangular guide, did all the separation of variables, found the possible solutions. At the end of the day, the thing you really cared about, is the characteristic of peaks of the guide versus frequency. You cared about the cutoff frequencies, right? Those are the two things. You could get the velocity propagation or the velocity, phase velocity, all that stuff you can get from beta. But those are the critical things. Now, there's a lot of math in between the beginning and where we end, right? And the math is important to have an appreciation for it, but it's not essential to be able to recreate that, all right? You just have to know where everything comes from. Now, here, when we're talking about antennas, I'm going to start by trying to do this in a way that will make sense to you. If you don't remember back in the days when you did statics, if you could say that the electric field was equal to minus the gradient of the voltage. How many remember that? Right? That's fundamental. Voltage is a scalar quantity. The electric field's a vector quantity. It's much harder to find the electric field from a set of charges or a charge density profile than it is the voltage. The voltage is easy to find. Then you can take the gradient of voltage. Now you need a mathematical formula for the voltage for any charge distribution, but you can easily take a gradient and get the E field. It's much easier to get the voltage and take the gradient of the voltage times the negative sign and get the E field. That's true. You remember doing this, right? How many remember at least calculating voltage, right? Voltage is something with scalar. We like scalar terms, at least I do. Now, when we calculate the electric field for propagating waves from antennas that launch waves, what we like to do is find a potential like the voltage that we can simply do a curl on or a gradient on and get the term we want, E or H field. You all follow me? So this is the idea behind this. So if you have just a small chunk of current, say it's actually just dl in length, and the current has a value of say I0. So this is a differential amount of current just existing by itself. We'll call it at the origin. And you come out a distance r away, there is something called the magnetic vector potential, the symbol is A. It's in your book. Actually, this would be a differential magnetic vector potential. dA is simply equal to mu0, and it's I dl. It is a vector, so the dl, there's a vector sense to this. If it was in the z direction, it'd be dz az. You all follow? It's going to be divided by 4 pi r. Then it's multiplied by e to the minus j beta r. Now that's called a differential, that's the actual magnetic vector potential, but it's the differential of it. the total A field,
E to the minus J.
beta R. And let me give you a page in the book so you'll have an appreciation for this. And Dr. Whitman's treatment of this is a bit hard to follow, but we all try our best. So he's going to show you what I'm trying to talk about. Starts on page 438, and it runs into page 441. But don't worry about that, just listen to me. So this magnetic vector potential, by the way, it is like a scalar because it only has a term, one term, in the direction of the differential current, all right? So if it's in the AZ direction, we have only one term, not generally three. Y'all follow me? When I have this is really equal to mu, well, I'll put it this way. It would be the integral of mu 0 times I, and I could be a function of position over 4 pi r. Could be a function of z. Then it's going to be times dl, whatever that is. Well, I'll just leave it like that. It could be a function of everything, actually, times e to the minus j beta r. And we go from, in our case, minus L over 2 to L over 2. If we assume the z direction, we might as well leave it in there. But that would be it, and then this would be dz, actually. And it would be in the AZ direction. Now, why did I do that? Because the B field you can get by simply taking the curl of A. Actually, I don't know, I really don't want to go down this road, but you know, a vector is uniquely defined if the curl and the gradient of that vector are defined. Then the vector is unique. Y'all follow me on this? They'll define the curl of A as B, and it is, by the way. This does work mathematically. And then they'll have well, I'm not going to do that yet. I'll just leave it at this. And also, by the way, since B is equal to mu h, you can get the h field here by saying it's 1 over mu times curl of A. Now, this is easy to get for current distributions. All right? We can get that, and we can take a curl of that to get the E, get h, and then we can simply take another curl of that to get E. Y'all follow me on that? It's basically, we can do derivative operations to get the final thing we're after. I'm going to take you through this, but please, if it seems a little mathematically too intense or bothersome, just go with me on this, I'll make sense of it. So, now we're going to take a look at this dipole right here, but we're going to look at the short dipole, and I'll do it right there. And what I want to do is first calculate A, the way he does it in his book, then calculate H, and then E, and show you how we do the far field assumption. I think it was 438, isn't that right? Anybody else got it in the book? I think it starts at 438. Okay. That's where he's gonna, well, I think and his is gonna get a little tough to understand. But just bear with me. All right, so now, pay attention to this. This is the short dipole workup. So for a short dipole, we have something, and it's electrically short. Its total length is L, but L is going to assume less than lambda over 10. So it's less than a tenth of a wavelength long. On this thing, we're going to assume the current is uniform in magnitude. Right? It doesn't have any kind of gradient spatially. The vertical axis, we'll call this the z-axis right there. Then we're going to come out. This will be the angle theta with respect to the vertical direction. Distance r away, and the first thing I have to do is I'll say, if I have a little differential chunk here of current, that can be dz thick, and it has a value of I, then I can say the differential magnetic field out here has to be in the direction AZ. So the differential magnetic field for this would be mu 0 I, it's going to be the same everywhere, so just I, times dz AZ over 4 pi r. Then it's going to have the form e to the minus j beta r here. Now that's the differential field. To get the total field, I'd have to integrate. I want you to listen to this. Some of this stuff you have to take on faith. All right, so to get A, I'm going to go ahead and integrate mu 0 from minus L over 2 to L over 2. Mu 0 I, it's a constant, doesn't matter. dz over 4 pi r. And we've got AZ e to the minus j beta r. Now, because this is a short dipole, where this itself is less than 1/10 of a wavelength, the distance out to here, we're gonna assume one thing, that r is gonna be much greater than the actual length of the antenna. If we don't do that, then we run into mathematical problems, which would be too close. Do y'all follow me? So this is really, you're far enough away so that you don't have to worry about, you might say, the overwhelming near field effect. If I'm right here and I'm calculating this, then all of a sudden, I have a big problem. There's gonna be all sorts of problems, and we have to watch out for singularities. But we're far enough away that we're not going to have to. And basically, because this is not even a 1/10 of a wavelength long, the distance from here, the top of this, out to my point of observation, it will be no different than the distance from here in terms of just r away, all right? They'll be approximately the same. And it has to do with that assumption that we're much less than 1/10 of a wavelength. What happens to this equation, the one place you can get stung here is this beta times r. Well, beta is 2 pi over lambda times r. If all of a sudden r changed and it was near an order of a wavelength, then beta times r here would make this term, the phase on that term, change quite a bit. Right? But we're assuming that we got a real short, electrically short dipole. What that means is this entire thing simply breaks down to this. After all that talking, I naught over 4 pi r. The r is effectively a constant. There's no real significant change. You can just write e to the minus j beta r here. And then for AZ, it's just in the AZ direction. Now here is where we do some things that, and this is in his book, here's where we do some things and we're going to adjust it for the coordinate system. Please appreciate this. So if I have a unit vector in the AZ direction, I'm trying to exaggerate this, it's a unit vector of length 1. If I take the projection of this on the r direction, this would be AR, it would be AR, AZ itself, I'm sorry, let me do it this way. AZ itself would be equal to AR cosine of theta, and then you would have the projection in the A phi direction this way, and it would be minus sine of theta A phi. Now, that does work, and it's really, that's AZ, if you take a look at this. The projection of this vector on this axis, if this is 90 degrees, would be a cosine term, and the projection on this axis would be minus the sine of that angle. And if you want, a good question is, well, how do I know it's a unit vector? Well, if you square this term and square that term and take the square root because they're orthogonal, you get 1. You all follow me? You get sine squared plus cosine squared, which is 1. It is a unit vector, and it works. And here's the other thing, always test yourself with this kind of transform. If theta was 0, it better be all AZ. Do you all agree with me? If theta is 0, I'm going right up sure enough. Cosine of 0 is 1, sine of 0 is 0. It is in the AZ direction. If it was 90 degrees, then it would be all A phi. You all follow me? So make it 90 degrees, cosine of 90 is 0, sine of 90 is 1. It would be minus A phi at 90 degrees. You all follow me, class? So keep that in mind. Go back to here, and now I change this AZ to cosine of theta AR minus, he does the same thing by the way, sine of theta A phi. So that's A, which happens to be also equal to, well, actually the curl of A will be equal to B, or curl of A divided by mu 0 will be equal to H. So now, obviously, if this is A right here, my next step is to take the curl of A and divide by mu 0 this term. So I'm going to do this next. Alright. So finally, I'm going to go ahead and get H now. And that means I have to take 1 over mu, I'll call it mu 0, times curl of A. We can do the whole curl if you want. And you know, if I'm doing a curl in cylindrical coordinates, If you look at the back of the book, right here, the very back of the book, he has the curl, and he has it in my book in cylindrical coordinates shown, but it's wrong in my book. So you better don't take the actual, the curl in Cartesian coordinates is right, but in cylindrical coordinates, see, if you look at the back of your book, if you have your book, just for a second, mine's at the top, it's on the back cover, inside part of the back cover. And where it says cylindrical, do you see it's got Cartesian coordinates there? Is yours? It doesn't. That's Cartesian. Okay, I guess your book's corrected. This is an older edition, it's not correct in here. But anyway, when you do this, the curl of it, I don't have the equation number for this, but it's in Dr. Willer's book. In my book, this is actually, this equation is wrong. When we do the curl of this, the entire curl, you're gonna get this term, you're gonna get beta, you're gonna get I times L beta squared over 4 pi. That comes out the front. And I divide by mu 0, so there's no mu 0. Then you're going to get the e to the minus j beta r, and then you're going to have the grouping. You're going to have j over beta r, and it's going to be plus 1 over beta r squared here. And then it's going to be times the sine of theta in the a phi direction. And I'm trying to keep this consistent with the way he put it in his book. Now, I'm going to explain something to you. We could take time to do that curl. Takes a little bit of doing. You can do that on your own if you're interested in it, but this is what the results of that are. You'll notice it's in the phi direction, a phi direction. We started with a over here that had 2 components. When you take the curl of it, you're only going to have this result. Now, here's something real important. You'll notice there's 2 terms, right? By the way, in my book, he has a j here. It's wrong. I'm going to tell you what equation that is. There shouldn't be a j there. I was looking through this, and I usually, when I do this, I don't even reference his book, but I've learned that because he has information in his book that students are going to look at and assume absolutely true, if there is an error, I better let you know. So in my book, it's equation 8.46. If you turn there, you're going to see that he has a j there. That j does not appear. Do you have that problem in yours? 8.46? Yeah. Is there a j there? It shouldn't be. There should be a j there, no j there. Okay. And if you look at the equation above, that one is correct that he gets it from. He forgets to get rid of that j. That's on him. Okay, now, when you look at this, there's 2 terms. You'll notice for this term, you got a term falling off as 1 over r right here and 1 over r squared. Y'all follow me? The 1 over r squared term has to do with the near field energy of the magnetic field. The 1 over r term has to do with the propagation effects. Y'all follow me? So the way we find it, where the breakpoint is between the 2, we know when magnitude of j over beta r is greater than the magnitude of this, 1 over beta r squared, this defines the point where all of a sudden we're in the far field, where now that term is going to dominate. Y'all follow me? Because the 1 over r squared, the 1 over r term will come down slower than the 1 over r squared term. Follow me on this, everyone? So if I go ahead and I take this, since it's magnitude, I can get rid of j and just leave it as 1. Then multiply both sides by beta r, and I get 1 is greater than 1 over beta r here, and that means that r is greater than 1 over beta, right? And that means that r is greater than, well, beta is 2 pi over lambda, or lambda over 2 pi. And this is called the far field. This is the point that defines the far field, or far field region. So when I'm at any distance r greater than lambda over 2 pi away from an antenna, I can assume most of the electric field strength and therefore the electromagnetic power density and energy is propagated. It's not coming back. Y'all follow me? And this is an arbitrary thing, but it's an important point of distinction. So anytime you have measurements on an antenna, if you want to be in the far field, you calculate with this, if it's a straight wire antenna, you calculate what this distance is, and you multiply it by 2 or 3. You want to be at least that far away when you talk about far field measurements, and we'll get into that more in a bit. Everybody got that? All right, now, once we have that far field down, and we've got the H field, here's what usually happens. And this is the easy way to do it. And I think you're going to appreciate the way I'm going to do this. I'm not going to take you through curl, because here's what I mean. If this is the H field, right? If that's the total H field, how would I get the E field? We can assume sigma 0. Well, what is the E field? Think about it. Curl of H, right, is equal to normally J. If conductivity is 0, then you get J omega epsilon times E, right? So to get the E field, you would take curl of H divided by J omega epsilon, and that would give you E, right? Y'all follow? Well, that means we have to take another curl of this thing, which just looks like so much fun. I really can't wait to do that. You don't need to do that. Here's what we normally do here. We say we're going to assume far field. Got it? So I'm going to write it down. We're assuming we're in the far field. Okay. Then what we do is this. That means we're assuming we're at r greater than lambda over 2 pi. And then in the far field, well, there is a beautiful relationship. And that is that the E field is simply equal to eta times the H field in terms of its magnitude. Now there is a correction for orientation. The H field's in the phi direction, the E field will be in the theta direction. Y'all hear me on this one, class? They have to be orthogonal. But you remember, for plane waves, if we're in the far field, we're talking about plane waves. And therefore we can get the E field by just taking that H field in the far field and multiplying it by eta and making a change on the angle, or a change in the orientation. Y'all with me on this, class? So please hear me on this one. So instead of going through another curl, which we could do if we really wanted to do it, and then finding the far field term, we can also get it this way. And I can say, and this is the thing you write down, the E field, and this would be for a short dipole. Remember, short dipole means the length of the dipole is less than lambda over 10. That's a rule of thumb, but it works. You can simply say it's equal to J, eta, has to be thrown in there, beta, I naught times L over 4 pi r. Then it's going to have the e to the minus j beta r term, and we'll have a sine of theta in the a theta direction. It's not phi anymore. Now, the theta direction, you can kind of reason your way through this, but you know that E cross H is the direction of propagation. Follow me? If the H field is in the phi direction, and it's propagating in the R direction, the E field has to be in the theta direction, so is a plus or minus theta. Use your right hand. All right? E cross H. H is in the phi direction, has to be, so E has to be theta. Y'all follow me on this, class? And that is really the E field from a short dipole oriented in the Z direction at the origin. So we're assuming our little short dipole, I naught current, total length L, at the origin, that's R, this is the Z direction going up, and we're assuming this is the angled measure, theta. That's it. Now, I didn't go through all the steps of curl. It used to drive people. Every time I did that with students, they looked at me with spite they hated. I'd ask them for homework to do the whole thing. And no matter what I said about how good it is for you to do this just once to really appreciate it, they'd look at me with total disgust. Like you ask us to waste our time. Nowadays, you know what you can do? Does anybody here use Mathematica at all for anything? Well, I know you can do it with MATLAB. I think has symbolic ways of doing this. Mathematica is beautiful. I write this thing, and then I type in cylindrical or indicate cylindrical course, just type, I just have to type curl of that, boom, out it comes, and it does it for me in a heartbeat. Then I can divide by J, make it epsilon, it does this, it groups everything together, it's a godsend. If you ever have to do any kind of crazy, or empirical solutions or empirical forms of curls, divergence, all that, use Mathematica. You'll thank me, you'll write me a letter. It'll save you weeks of anguish. Okay, so that's the E field for a short dive. Now, we're not quite done with that. So now, the next thing, if that is the E field, I should have left it up there, but I need this board and this board for what I'm about to do. The next thing you gotta do is find the power density. Now, average power density. We're assuming we're in the far field. When we talk about power density, or PAV, right, normally it's one half the real part of E cross H conjugate. That's the normal way you do this if we're in the phasor domain. Y'all follow me? But if we are talking about propagating electromagnetic energy, then I can say this is equal to simply 1/2, right? Magnitude of the E field squared over eta naught, and it would be in the AR direction if this thing's at the origin, or we can say it's 1/2 times eta naught times the magnitude of the H field squared. Either one will get it, and we'll be in the AR direction. Everybody with me on this? I could go ahead and do this, but it will give me this or that, guaranteed for far field, and we're only talking about far field. So for PAV here, if I do this one, I get eta naught over 2. Now the H field was what? It was beta times I naught times L, right? Over 4 pi r. Remember, it's going to be a magnitude, so the phase term you can forget about. Then you're going to have sine of theta. And this is only the far field term. It would be AR. Now the only thing I've done is I've taken, I know what the H field is, you may not, but you just take the E field and get rid of eta naught and you got the H field. And I don't care about the phase stuff, I don't care about that J or E to the J beta, because it's going to be magnitude. Then you got to square it. So this comes down to eta naught over 2. Then I'm going to have beta squared, I naught squared, this is in his book by the way, but he doesn't do it this way, L squared, divided by 4 pi squared, divided by 16 pi squared, r squared, and then it's sine squared theta. And that's in the AR direction. And that would be in watts per meter squared. It's in his book. It's equation 851. I prefer just showing it this way. I think he's got his 32 pi. I have 2 times 16 pi. But that's it. Y'all follow me, class? That's it in a nutshell. And that is the average power density. Now, if we wanted the total power radiated, we take the average, we take the power density and integrate it over the surface of a sphere. Y'all follow me? Yeah. So if I want total power radiated, what I do is go ahead and I say, it's the integral, double integral on this one, of the average power density. I'm just going to leave it as PAV. And PAV is a function of R and theta and all that other stuff. R, theta. Alright? It's going to be this is in the AR direction. Then I got it into the surface area of a sphere. The differential surface area on a sphere is R squared times the sine of theta, d theta, d phi. Theta in this one would go from 0 to pi, and phi from 0 to 2 pi. So the total power radiated, we could do this actually. I used to do this in class all the time. I would take this equation and I put it in there. You notice that all this stuff right here is a constant. You got a sine squared of theta over r squared. Y'all follow me? You agree, class? I'm just going to tell you, when you take the whole thing and do it, you get this. You get total power radiated for this to be equal to, and In his book, here's where it is, it's equation 8.55 on page 444, but it's 40 pi squared, and then it's going to be L over lambda squared times I naught squared. I think that's the form he has. Let's check on that. Yeah. All right. Please hear me on this one. This is important, what I'm about to say. Now remember, this is an antenna. We're talking about power radiated. It has to come from somewhere. It comes from the antenna current driving a real resistance. Y'all hear me? But that resistance isn't an ohmic dissipator. It doesn't dissipate in terms of turning the electrical power into heat. What it's doing is launching electromagnetic energy. Got me on this one? So they define that resistance as the radiation resistance. And they take this total power, and they say that's equal to 1/2 times I naught squared times R radiation. This is called the radiation resistance. And it is, in effect, the coupler. It defines the coupling between the electrical current and the amount of power radiated into the system. It's got to be an I squared relationship, I squared times that. Because it's got the 1/2 because we're talking about peak value. Which means the radiation resistance of the antenna, by the way, this is measurable, is going to be twice that. If you take a look at this, the I squared is going away, we have to multiply that by 2, and it's 80 pi squared times L over lambda squared. Now I'm going to make a comment here, and this is in ohms. First thing is, when you have any dipole, whatever the length, there's a radiation resistance. However, that radiation resistance may be much smaller than the actual reactance. You're going to have a plus J, all right, reactance. It's really going to be due to the inductance of the antenna. Usually, the inductance of an antenna, a short antenna, is going to dominate the actual value of impedance, the input impedance. It's going to be mainly reactive. Do y'all follow me? And dipole antennas are very poor or short dipoles are poor radiators. Now, give you an idea how small this is. We'd like it large, so we could have a small current generating a lot of power. We'd like that. But remember, I said L and lambda. L has to be only 1/10 of a wavelength or less, right? Follow me. That makes this 1/10 squared, 1 over 100 times 80, right? That's 8/10 or 4/5 pi squared. Well, 4/5 pi squared, call pi 3 squared, that's 9. 4/5 times 9, this is of the order of tens of ohms. Got me on this? And less. That's not much. You would like to have an input impedance higher, much higher, because that way a smaller current would radiate the same amount of power. And the more current, the more ohmic losses you have. Remember that. You're always trying to minimize the current needed to generate the power radiated. So that's that. And now I ran out of time as usual. I'm going to have to give you a quiz. I'll pick this up. I'm going to give you some homework to do for Monday, but I'll pick this up on Monday. I hope you have a great weekend. Please be safe. Don't do anything crazy. My town's going to be packed. I went to Penn State, and my brother's here. I hope we win. I mean, I hope Auburn wins.